Hello everyone, and welcome back to another Eng 130 video tutorial. So in this last tutorial this week, we're going to just cover a more practical example of solving a beam in equilibrium considering support reactions. So as you guys know, throughout the whole week, all we've been focusing on is support reactions, but now let's look at a problem that may be more similar to your homework or even the lab, where it's kind of you need the support reactions, but it kind of takes it maybe a step further, stuff like that. So hopefully this video can help you guys with those type of problems, and it's just kind of a nice way to end the week before the real fun starts. And the real fun is internal forces, so forces inside of a truss or forces inside of a beam, which is what you guys will be doing for the next 3 weeks. So just sit back, relax, and yeah, let's get started. All right, so looking at this example, it says a boom is intended to support two vertical loads, F1 and F2. If the cable CB, so if we look at the diagram real quick, that's talking about this cable right here, can sustain a maximum load of 1500 newtons before it fails, determine the critical loads if F1 is equal to 2 times F2. Also, what is the magnitude of the maximum reaction at pin A? So this question's kind of tricky because it says maximum. And I know that after the midterm, you guys are studying so hard and you guys saw all the maximum videos. You guys are thinking, oh, maximum, it's going to have to be, we're going to have to do the elasticity, stuff like that. But this is actually a bit of a different case. So the best way to show you guys is to draw a free body diagram. And you guys will hear me say that so many times because trust me, a lot of these problems can easily be solved with a good free body diagram. So I'm going to start with the beam. I'm going to put it at an angle, something like this. And that looks pretty good. I'm just going to move it down a bit. Yeah, so let's draw a free body diagram and just kind of see what happens. So this is the beam. If we look at point A, it's a pin, so we know it's going to have two reactions. It's going to have a vertical, as so, and it's going to have a horizontal. Just because it's a pin, so you guys dealt with pins this week, you guys know exactly where that comes from. If we look, there's also two more reactions at the beam. We have one about here, coming straight down, and we have one here coming straight down. So we should probably label these real quick. So at the pin, we know it's going to be AY. Over on this side, AX. We look up here, we got F2, and then we got F1. And then on this side, what we have is the cable. So at the top here, we know that there's a cable kind of coming like this. And we know that it has specific distances, which is 3, 4, and 5. And now we have to look and say, okay, well, we know that we're trying to find F1 and F2, as well as the pin, but when? And it says the maximum it can suspend is 1500 newtons. So I could put 1500 newtons right here. And now a lot of you guys will start asking me, Clayton, why aren't you putting 1 or something like that, keeping it elastic? Well, it's kind of hard to describe, but we're looking at the critical case right here. And this critical case will be when this one is equal to 1500 newtons. So that's kind of the nice thing is if there's only one cable that has the maximum, you can assume it's at the maximum. In this case, it's one cable. Now, if it was F1 and F2, and those were cables, and it said either one of those is a maximum, so we have more than one case where it's a maximum, that's when we're going to have to go to the elastic part. But in this case, only one thing has a maximum, so we can assume it's at the maximum. Everything else is fine. But now if we look at the diagram, we still got other problems real quick. We have 3 equilibrium equations, so the max we can solve for is 3 unknowns. But if we look, we have 4 unknowns, AX, AY, F1, and F2. So we have to look at the question, is there something to help us solve this? And there is. And because it says at the critical load, F1 is equal to 2 times F2. So instead of F1 down here, I'm going to put is equal to 2 times F2. Because now if we look at this, we're going to say, okay, we got F2, AX, and AY. So 3 unknowns, 3 equations. We can actually start to solve this. But before we do, we need to add a couple more things into the free body diagram, which are the dimensions. So we know that the beam is at 30 degrees. And we know that the span of the beam will be something like this. So it starts here, and we got F2 right there. And we know it's 1.5 meters and 1 meter. So 1.5 meters and 1 meter. All right, so now we can solve the beam. Now that we have all of our stuff in there. 3 equations, 3 unknowns. Let's begin. So what I like to do typically, take the sum of the moments at the pin. Because if I do that right now, AX is gone, AY is gone. Nice and simple, nice and easy. So if I go to sum of the moments at A equals 0, you'll see that it's going to get kind of messy because everything's at an angle. So what's nice is the forces are already vertical, so we don't have to really consider those. So let's start off with F1. And instead of F1, I remember that's equal to 2 times F2. So we're going to go 2 times F2, and we're going to want the distance. But remember, we're going to want that horizontal distance. We're not going to want any angular distance. So it's going to be 1.5 times the cosine of 30. And that distance is actually, and I'll show it on here, that's the distance from here over to the force. So this is the one we want when we're taking the moment, right there. Excuse me. All right, so now we can move on to the next force, which is F2. So we're going to go F2. And then for this distance, we're also going to want that horizontal distance. And in this case, it's going to be 2.5. So that's the 1.5 plus the 1.0 times cosine of 30. So not too bad. Now we got to ask yourselves, okay, what kind of moment do these forces create? Is it going to be positive? Is it going to be negative? Well, it's pretty simple. If I hold my pencil at A and I start pushing down at it, as we'll see, it starts creating that clockwise rotation. So both of these are going to be negatives. All right, so not too bad. But now we have to consider the cable force. And now this one gets a little bit more tricky because it's at an angle, so we're going to have to consider both the x and the y component. So it's going to be something like this, where it has a y component, and then it also have an x component. Oops, that does not look good. An x component, so something like this. So if we start off at the x component, it's pretty nice. So it's going to be 1500. And remember, we want that x component only. So to get that, we're going to go 4 over 5. So that's the x component. And then we're going to have to multiply it by the distance. So for the x component here, we're going to want the distance basically from here all the way to there, which we see is going to be 2.5 times the sine of 30. So I'm going to go over here, 2.5 times the sine of 30. So the tricky part to this one is just going to be figuring out all of those directions, or the distances. And if I were to look at the rotational tendency because of this, as we'll see, if I hold my pencil vertically and hold the bottom at point A, and I come in from the left, it starts creating that counterclockwise rotation. So this one's going to be positive. And for the next one, we're going to consider the vertical component. So it's 1500 times 3 over 5. And for this distance, if we look, it's going to be actually the same as F2, which is going to be 2.5 times the cosine of 30. And we know this is also going to create a positive moment. And all this is equal to 0. So if we look at this equation, we have one unknown, which is F2, and one equation. Very, very easy to solve. We can find out that F2 is going to be equal to 724 newtons. And that's just solving this equation. Now, it didn't just ask us for F2, it was also curious about F1. But what's really nice is the question really said right at the beginning, F1 is going to be equal to 2 multiplied by F2. So we're just going to go 2 times 724, therefore F2 is going to be equal to 1448, and it's going to be newtons. So I can box that in. The first part of the question is done. So it's, again, not that hard if you have the good free body diagram. So it's one of the things I want to try and really drill into your guys' head. You guys have a good free body diagram. All of the questions this week are just going to fly by. It's just simple equilibrium, 3 equations, 3 unknowns, just making sure you guys know exactly where those forces act, stuff like that. So now, since we know all those forces, we can start determining the support at the pin, which is AX and AY. So if I were to go sum of the forces, oops, I don't want to do that in red. Sum of the forces in Y, or actually, yeah, it doesn't matter which one you start with. Let's go Y, why not? Get it? Why not? Nah, too cringy. All right, so we see that when we're looking at Y, we got AY going up. So AY going up. And we got both F1 and F2 going down. So minus F1, which is the 1448, minus the 724. And we see that there's a component, the vertical component of that cable, that also goes up. So 15 times, what if we look up, it's going to be 3 over 5. 3 over 5. And that is equal to 0. So if we solve this real quick, what we'll find out is that AY is equal to 1272 newtons. Now, you guys notice that I didn't box this because this is not my final answer. The trick to this question is realizing it's asking for the magnitude of the maximum reaction at pin. The maximum reaction at pin A. So the magnitude of it is going to be similar to when we were doing vectors before, where if we know the x and the y components, well, we just figured out AY and we're going to find out AX, we can actually find the magnitude of just A in general, which is what we're going to want to do. So we're going to need AX. So we go sum of the forces. Oh, I got to remember to always switch back after. Sum of the forces and X is equal to 0. Well, it's not too bad because F1 and F2 don't have any components. So we got AX, and we assumed it's positive, and then minus 1500. So just the horizontal component of that rope, so times 4 over 5 is equal to 0. So AX is going to be equal to 1200 newtons. So now we have AX, AY. We can actually solve for the magnitude now, which is A, using the exact same thing we did before, where it's going to be the square root of all the components squared. So we're going to have AX squared, so 1200 squared, plus AY squared, so 1272 squared. I can bring the square root over, and in the end, I get 1749 newtons. So 17,400. So 17,400. No, 1,749. I don't know why that was so hard for me to say. So we come down to the bottom. We got A is equal to 17,400. Oh my gosh, I still said it again. 1,749 newtons. And I could box that answer. And if you guys look, well, you're going to go, okay, Clayton, well, you just solved for that. But it said the maximum reaction at pin A. So shouldn't there be a little bit of a trick? And really, no. Because since we have the 1500 as a maximum over here, we solved for A based upon the maximum criterion, which is the maximum load. So this is what A would be. Good to go. If I looked, I got A. I have F1 and F2. Ooh, but I didn't label them correctly. You guys. F1. This is actually F2. Glad I caught that. I know I would have gotten so many emails from you guys letting me know how dumb I am. So yeah, that's kind of a more practical example. But as you guys see, it's really, really easy. Really, really easy. So my advice to you guys, enjoy this week because it doesn't stay easy for long. We got trusses coming up next week. And those videos I already know will be lengthy, pretty beefy videos because trusses are probably one of the more tedious things you guys will see. So thank you guys so much for listening. Hoping you guys had a nice little long weekend, relaxed, ready to go because it's only going to get more and more fun from here. So thanks guys. I'll see you guys in the videos next week.